Hey, we're going to create an encryption system next. But before we do that, I figured it would help me out to go through some of the principles of the encryption. This is going to be an RSA encryption. And we're just going to run the script and talk through it a little bit. We're going to have two functions I created. One's called the GCD, the greatest common divisor. That would be the greatest common divisor between two ints, A and B. And then the inverse of E and N. Well, the inverse is something that takes an inverse is if I can take that E and multiply it by the supposed inverse and I can't say it, mod N, it should equal 1. So we're just going to find the multiplicative inverse of E and number mod N. And we'll use that so we can create our encryption E and our decryption D variables. We'll talk about that in a second. I'm going to start the script right now and just walk through it. So we're going to start the primary pieces of information I want to collect are prime numbers, because you're going to take two prime numbers. We'll call them, in this case, P and Q, and we're going to multiply them together, called PQ. Now you'll see this called N elsewhere, but I call it PQ because that reminds me of where they come from. It's just the product of P and Q. And this constitutes the hard problem in breaking an encryption. If you have really large prime numbers and you multiply them together, it's really hard for a computer to factor them out. And we're going to look at some really large prime numbers at the end of this particular demonstration. Anyway, we're going to take PQ, and then we're going to take this thing called phi, or maybe it's phi. I have a degree in math. I still don't know what it's called, but it's the totient between P and Q, and the totient is the number of numbers that are co-prime to P. In this case, since P is prime, the number of co-prime numbers less than P is P minus 1, and Q is Q minus 1. So the totient is P minus 1 times Q minus 1. And then the message, lo and behold, is going to be 42. We're going to encrypt 42 to a secret message and then decrypt it back, hopefully, to 42. I'm just going to print that stuff out right here, and I'm going to make this come up so we can see the screen a little bit better. The next thing we're going to do is find an E. I use the variable E to mean encryption, the encryptor, the thing you give to the public to encrypt with, along with the N or the PQ. I believe the RSA documentation had key E and D backwards. E encryption, and anyway, let's talk about E for a second. E is just going to be a number that's co-prime to phi. It could be a prime number, probably should be a prime number, and something probably greater than 2. 3 or greater will be fine. So I'm going to random int to look for an E. I'm going to look to see if that number is what we want. And if it's the greatest common divisor is 1 between this number and that number, then I'm going to break as I found it. Found my E. My E is 1349. Haha, we found it. So the next step we're going to do is try to find that inverse. Now, an inverse is something that when you take E and D, we'll call it D for decrypting. You multiply E times D and you modulo the phi, it should equal 1, an inverse. That's why we call it an inverse, D. So found a D is 7565. Right here, I'm actually going to calculate that to prove that out. So when I click this next bit here, I say E is what we found and D is the one we found, and we do the calculation, and it does in fact equal 1. So this will work for our encryption. Now with this we create our public key. And our public key is simply that E we found first, along with the N or the PQ number right here. So we have E, this is we're going to give our public key to anybody. So they'll take their message, they'll take the E and then raise that to take your message, raise it to the ETH power, F power, and then mod the PQ or N number, and that'll be our encrypted environment. And then once they've done that, we can take their message and having problems with the standard out here, sorry, and take our private message and decrypt it. And that's what we're going to do right here. So I'm going to take that message, which hopefully you can see is 42, raise it to the ETH power, all that mod PQ, becomes our encoded, and it turns out to be 707. So 42 is encoded with our public key to 707. Now I can take that 707, raise it to the dth power, modulo mod PQ, and that should decode right back to 42. And if I hover enough, it says 42. And there, it says I encrypted 42 right here. I'm encrypting 42. I encrypted to 707, and it decoded as 42. And that demonstrated basically the whole premise of the encryption. Now, when we encrypt, we're going to encrypt with larger numbers. We're not going to use small prime numbers. And right now, I'm just going to click the go button, if you will, to get stuff. I'm generating 3 prime numbers. There they are. They came out pretty fast. 300 digits length, 350, and 400 digits. Go to the right of the standard out. You can see that they're fairly large numbers. Want to demonstrate a problem in basically the management of your keys when we create keys. Mostly as a reminder to myself is basically don't reuse keys. So it takes effort to create these keys, and if I reuse the keys like this, I'll just do it here. I'm creating PQ and PR, so I've named my primes P, Q, and R. PQ is P times Q, QR is Q times R, and I'll print them. And here is basically the hard part of our keys. We'll create E for that to give to somebody, but look how long that is. That's a huge number. It's incredibly hard to factor this out, and we know that these are prime. So we know that this was probably, 600 digit or more number to factor out. That's going to take a computer a long time. Well, what's the issue here then? Where am I? I'm up here. Anyway, I'm just saying here, this constitutes the RSA problem with factoring. You can't factor that. But if I share my keys or my prime numbers between keys, watch this. All I have to do is factor this using a greatest common divisor, and bam, I've just factored Q, just factored P out, factored R. So if I distribute this P, Q, and QR out into my schemes, a cracker can just take the public key and factor out my prime numbers. And let's see if it found it for real. So what this next step is going to do is to say is P equal to P factored, Q equal to Q factored, R equal to R factored. And it's just going to evaluate that expression. So we can see boom, boom, and boom. Hey, true, true, true. Reusing prime numbers and different keys will totally make your your encryption system worthless. And we just simulated that. Anyway, in the next couple of videos, we're going to go through and actually create an RSA system. But we'll start with building keys, and then encryptors, and then key management system, and then end with encrypting stuff that we use in some of our scripts. Anyway, the whole script is right there and is fun to play with. And anyway, demonstrates, remind me how this works, and I'll sign off for now.